From the speech of a single pipe to the massed ranks singing together, the organ's vast potential is shaped out of thin air. But how does music come from the shaping of the physical world? Physicist George Plitnick.
Sound can be considered as being composed of three areas: noise, language, and musical tone. Noise is a random, erratic type of oscillation.
Each end of the string is fixed. They're points of no vibration, the nodes of the waveform. In the center is the point of maximum vibration, the antinode. From node to node is the wavelength. It's the wavelength that fits on the string that determines the frequency or pitch of the note we hear.
The second way of generating musical tone is in the vibrating air column. Now, we can't see the vibrations in the air column as we can on the string. Nevertheless, there are points of no vibration, called nodes, and points of maximum vibration, called antinodes.
The organ pipe is engineered to create and contain a vibrating column of air. Like the string, the length of the pipe determines the length of its wave, and that wavelength determines the pitch of the sound we hear. A pressure microphone can detect the wave in the pipe. The oscilloscope shows no vibration. This is the node. Further in, the vibrations increase as the microphone moves towards the middle of the pipe. This is the center of the waveform, the antinode, the point of maximum vibration. This invisible wave is shaped by the length of the pipe to create its pitch. Every pipe in the organ is the physical shape of the pitch it produces, and there are thousands of them. These multitudes are the frozen forms of music itself in all its incredible range and variety. What gives each instrument its characteristic sound? Why does the violin sound so rich and the flute so haunting and hollow? It's because they don't produce pure sounds. Every note they make is a combination of many different pitches. When a string is plucked, we can hear its fundamental pitch. But we can hear other pitches too. The pitch of a string, half as long, can be heard on the long string. The long string produces both pitches at once, as though the strings were being played together. So, as well as the fundamental wavelength, a wavelength half as long fits on the string. Both these frequencies can be heard together when a single string is plucked. This is the special nature of a string that allows it to create a complex musical tone. It can vibrate at several frequencies at once because many different wavelengths fit on it. In every musical tone, we hear those frequencies sounding simultaneously. The sound of the long string also contains the pitch of a string 1/3 as long. Its pitch sounds when the long string is plucked because its wavelength also fits exactly on the string. This physical relationship is the basis of musical tone. It works the same way in a vibrating column of air. This pipe contains cork dust. When a musical tone is put through it, the dust will show the complex waveforms that all occur simultaneously within the pipe. These are the shapes of musical tone. Each instrument manipulates them differently, combining more of one frequency, less of another into a unique structure of overtones. The simplest of musical sounds, a pure pitch. On the spectrum analyzer, it has one frequency, the fundamental. The flute creates a more complex spectrum of sound. It's built out of a strong fundamental pitch and a number of weaker overtone frequencies. In every note of the violin, we hear the resonance of powerful overtones. It's a rich recipe for musical tone. Every instrument has its own unique sound, created out of its overtone structure. But the organ exploits all the possibilities of musical tone, sculpting a spectrum of sound in every size and shape. It creates a bewildering array of tones and colors, including the sounds of many different instruments in its endless repertoire.